All right, let's try again. Let me know immediately if you cannot hear me. So basically, we wanted to look at the numbers and see what kind of cues can we get
Sir,
practically.
your screen is not visible here. Your
Oh,
screen
screen,
is not
yeah,
visible.
sorry, yeah, I forgot to share.
Thank you, sir.
Is it showing? Is it clearly visible now?
Yes, sir, it is.
Okay, good. All right. So basically, we wanted to take a look at some numbers for some practical cavities and see what kind of cues do we get and how do they compare with your standard LC circuit cues. So we want to design a cavity using copper to operate at 10 gigahertz. So basically, we have to design. Again, we want to use a cubic cavity because that gives you the best cue for rectangular shape. And we want to find what the Q is. So because we are designing for the cubic cavity, A is equal to B is equal to C. And yesterday we had seen that there are three different modes which are going to be present. Either the TM110 mode or the TE011 or the TE101 modes. And in fact, these modes are exactly the same modes, it's just with respect to the direction. It's the direction of the electric field is changing uh, in X, Y, or Z, what we are calling X, Y, or Z. Practically speaking, they are effectively the same modes. Uh, so we want the frequency F to be 10 gigahertz, and let's assume TE101. We would get a term which would be given by that, just substituting the term. So 1 by 2 pi square root of mu naught epsilon square root of m pi by a square plus n pi by b square, b is equal to a, plus p pi by c square, c is equal to a. Uh, so if we substitute those terms, just do the mathematics calculation, we find that a is equal to roughly 2.12 centimeters. So about half the size of a thumb, uh, just to put things in perspective. So a cube, which is about half the size of a thumb, would this dimension be? This cavity would be of that size. Let's calculate the Q for this cavity. Q is, as we have seen before, would be pi F101 mu naught A by 3RS, and substituting the value of RS as square root of omega mu sigma, we can write this as A by 3 square root of pi f 101 mu naught sigma. And sigma for copper is roughly 5.8 into 10 to power 7 Siemens per meter. So when we substitute these terms, Q, we'll see Q would be approximately 10,700. This is much larger than the LC resonance circuits you have seen in your circuits course. LC lumped element resonant circuits. In those circuits, you're lucky to get a Q of about 10. Here, the theoretical Q is approaching close to 10,000, is slightly larger than 10,000. In reality, we won't get this Q. And that is because when you're making these cavities, you're making it with metal. The metal is going to have some surface roughness. So the metal is going to have surface roughness to them. Again, remember, in all our calculations, we have assumed that the metal is nice, which provides the electric field, and thus the electric field has to go to zero right there. But in reality, the metal would have some surface roughness around, and wherever there are some sharp edges of the surface, now that boundary condition is slightly broken. Because of this surface roughness, there would be some localized electric field here. Ideally, that electric field should be zero, but because of that surface roughness, that parallel boundary condition is not met at every single point. So there would be some localized electric field and thus some magnetic field present at that place. So in reality, because of these surface roughness issues, the Q tends to be approximately 5,000 to 6,000 range when we fabricate it. To increase the Q further, you can gold plate the inside part of the copper. Gold has a much higher sigma compared to your copper. So you can gold plate the inside part of the copper to achieve higher values of Q within these cavities. But nevertheless, even if you do a really bad job, you still get Qs which are higher than the Qs you get with lump circuits like L and C circuits, which you probably have seen before. So these are decently efficient values. Let's consider now the next cavity. These rectangular cavities are again, they are rectangular cavities, but not the most preferred cavities. The next cavity, which is normally the most preferred one for its simple design and how the fields are related, is the circular cavity resonator. These circular cavity resonators are again basically, as you may have guessed it already, is a circular waveguide with metals on the top and the bottom too. So it's a circular waveguide with conductors on the top and the bottom. And you would expect for same volume, surface area is going to be smaller than cube, again remember the circumference of a circle is smaller than the perimeter of a square for the same area. So you expect that the volume of this would be smaller than the surface area is going to be smaller for the same volume than the cube, and hence what you're going to see is expect higher Qs compared to cube. So let's look at what kind of modes exist. We have already calculated the modes for a circular waveguide. Let's define that we have a radius of A. We have a radius of A, and let's assume that this height is some arbitrary height D. So it's a small cylinder with a cap on the top and the bottom. And inside this, so basically this is a thin wall conductor, and inside that conductor you fill it with a dielectric, sometimes hollow, other times some material which is mu and epsilon. So now we know for the cylindrical waveguide, again we are looking for the lowest order mode, which has energy or field density, field peaks in the center. We don't want this to move towards the outside. Don't want the field to move towards the outside. The field has to be within the center. Well, the lowest order mode which happens in a circular waveguide is a TE mode, where n is equal to 1 and p is equal to 1. So TE11 actually has a lower cutoff than a TM mode. But the TE1, the electric field inside the center is 0 and all the field is pushed towards the edges. So we expect that to be lossy. So we want to operate it in the TM01 mode of the waveguide. We want this to operate within the TM01 mode of that waveguide. Again, let's quickly remember what TM01 means. 0 means no change in azimuthal direction. That there is no change of the field values, field amplitudes as you go around in a circle. There's no lobes which are created there. So there's no change in azimuthal direction, and hence the Bessel function has to be J0 function. They are related. And the 1 means we are going to the first 0. Of the J0 HR function. Remember, we have the term Ez in the TM01 mode that in terms of the cavity is a field pointing in Z direction We have the term Ez, which we had seen was a function when m is equal to 0 was just a function of some constant and j naught with the argument hr, and this function of Ez had to be 0 at r is equal to a. This function had to be 0, so j naught ha had to be 0, and we went to the first 0 of the function j naught, and we had seen that the first 0 happens when ha is 2.405 or h is 2.405 by a. So you get the term Ez as C naught. This is coming directly from the discussions we had in circular waveguides as J naught 2.405 by AR. With respect to Ez, we had also seen that there was an H5 field. The H5 field was turning around this way, and then there was an ER term. And we had seen that the H5 field was basically the derivative of the J function, J C naught by eta naught, J naught prime HR, where eta naught was the impedance of the material we have used. Using the identity I had given you before, J naught HR is half of J 0 minus 1 minus 1 HR minus 0 plus 1 plus 1 HR, but J of minus 1 HR is equal to minus J of plus 1 HR. Again, remember J of minus N is equal to minus J of N. Again, Bessel function is nothing but an expansion function. So if you multiply it by 1, the terms which were positive become negative, the terms which were negative become positive. So the result is just minus. So now basically you have J naught prime HR. We can write J naught prime HR as nothing but minus of J1 HR. You get minus of 2J1 HR from this term divided by 2. So you get minus of J1 HR. So H5 term is now becoming plus J minus minus becomes plus C naught by eta naught J1, and H can only take the value 2.405 by AR. Let's look at these terms and let's see what they look like. So far what we have realized is two things. One is that I have Ez term which is pointing in the length direction of the cavity. That is given by C naught J naught 2.405 by AR, and I have H5 term which is given by J C naught by eta naught J1 2.405 by AR. Two things you notice here. is that these two again are in quadrature phase. We have the j term show up here too, which is ej pi by 2. So they are off again in quadrature phase, which tells you that the power is not going to go anywhere. The power is just going to sit within the structure. So if I look at this variation now, if I look at it from the top view into the cavity, what I have, let's say this is the conductor. I have E, which is pointing in the Z direction. So the E is going in the Z direction. And I have H, which is pointing in the phi direction, is turning around in the phi direction. So if I was plotting H, let's plot H with red color. This plotting H, it's saying there's some constants. There is some function J1. J1 function we know has a 0 at r is equal to 0. And the J1 function increases as your value increases. So it's telling you that there is no field happening in the center. The field would start from the side. It will be weaker in the center, so further spaced apart. And as I go towards the side, the field will become closer and closer together. This is your H field. H in the center would be 0. That's the J1 function. The J1, except for J0 function, every other order of J, every other order of Bessel function for n to be integer has a value of 0 at the center. So that becomes your J function. And then your E function is a function which is coming outwards. And E function has is centered at it has the function j naught. So it's telling you E function is stronger in the center. It's going to be much closer in the center. It's going to have a value here. It's going to be much closer in the center. And as I go away from the center, these field lines are going to be going out, are going to be spreading out. And again, the E value here has to be 0, and which is true because E is parallel to that place. So the E value there has to be 0. If I take the longitudinal cut, let me put it in another slide. If I take the longitudinal cut, and see what is happening around, then what you're going to see is, so I have this cavity here. I take a cut around, and then I just plot that cut. I have, because it's a cylinder on that side, the cut is going to look like this being the outer edge being the metal. This height is going to be D. This width is going to be 2A. And what this is telling you is that the electric field is pointing in Z direction. The electric field is pointing in Z direction. It is much closer in the center. This point in the center is r is equal to 0 point. It's much closer in the center, but as I go further away, this starts to spread out according to my J function. However, now if you notice in the vertical direction, this field can be supported. All this field is doing is putting some charges, induced charges on the top and the bottom surface. That field is hitting the conductors at 90 degrees. So that field is still supported by the cavity. And there is no variation in the z direction. The amplitude doesn't vary in the z direction. Thus, the mode which is supported, the mode which is dominant, is what we call the TM010 mode. The first zero represent the no change in azimuth. First zero of J0 function, which happens at the value of 2.405, and the last zero represents no change in z direction. There's absolutely no change happening there. So that is the fundamental mode which is present within this cavity. And again, it's not trivial to calculate the Q, so I won't go through those calculations. You need to know the integral of the J functions, which haven't been done. But the Q for this mode, so I'll just give you the final relationship. Q for this mode would be given by eta naught by Rs 2.405 by 2 1 plus A by D. And this is your TM010 mode. So basically in the TM010 mode, why we chose TM01 mode is because in TM01 mode, the field is present in the center of the cavity. It's not pushed towards the side of the cylindrical walls. And because in TM01 mode, the field which is present is an EZ field. There's an ER field too, which doesn't get affected by conductors, but there's an EZ field. The field which is present is the EZ field. That EZ field is going to be perpendicular to the top and the bottom conductors. And because of that, that field is still going to be supported. So things are actually easier to calculate that way. And also the frequency of this TM010 mode is just going to be this last putting Z did not really change anything on that frequency. The electric field was pointing in that direction. That electric field was still allowed. So this would become F would become TM010. So that would be 2.405 divided by 2 pi a square root of mu epsilon in terms of the hertz. Let's take a look at the same terms and let's compare a cylindrical cavity with a cubic cavity before, what we had done before. So we want to compare this circular cavity or cylindrical cavity with cube. So if I want F resonance to be 10 gigahertz and mu is equal to mu naught, epsilon is equal to epsilon naught air filled cavity, then my FTM010 would be given by 2.405 2 pi a into c, being the speed of light. And if you calculate a would be approximately given by 1.15 centimeters. That would be the radius we had. If I look at the diameter is 2 times a would be 2.3 centimeters. Remember, for cubic cavity, the one side length, which we had called a there, was approximately 2.12, yes, 2.12 centimeters. This is a circle, this is a cube, right? So the surface areas are going to be different. If I calculate my Q, Q would be given by my eta naught by Rs 2.405 to 1 plus A by D. And normally, let's assume that your D is equal to the diameter, so D is equal to 2A. So D is 2.12 centimeters. Your RS is square root of pi F sigma by mu naught by sigma. And if you substitute the values, this would be 2.61 into 10 minus 2 ohms. So your Q turns out to be eta naught, which is 377 ohms, divided by 2.61 into 10 minus 2, 2.405 to 1 plus A by D, which is 1 plus half. And this turns out to be approximately 11,580. So if I summarize, let's put it in the table and see what differences we see. If I take the circular cavity and the rectangular cavity, if I look at the resonant mode, the preferable mode for the circular cavity is your TM010 mode, which has two components Ez and H phi. And in the rectangular cavity, you have TE101 mode. If I'm operating at 10 gigahertz, you'll see that the dimensions we saw were roughly the same. We said the diameter D is equal to 2A is 2.30 centimeters. and the length we said was twice again 2.30 centimeters. This is the reason I chose, because it's looking more like cubic dimensions then. And in this case, the dimensions A, B is equal to C were 2.12 centimeter. If I compare the volume here would be pi A square D, and this would be approximately 9.56 centimeter square, where the volume here would be A cube and would be approximately 9.58 centimeter cube. So you see, the choice I made in this example was to have roughly similar volume for both the cavities. If I look at the surface area, on the other hand now, surface area would be the surface area of the two plates on the top and the bottom, plus the surface area of the circle part, which would be 2 pi a into d, and this would be approximately 24.93 centimeter square. Whereas the surface area here would be 6 faces of the cube multiplied by a square, and this would be 26.97 centimeter square. So you notice the volume is roughly the same, not much change, but the surface area is smaller than the surface area you have on the other side. The surface area for circular cavity is roughly 8.2% smaller. So surface area for circular cavity is roughly 8.2% smaller than the cube. And because of that, you have your Q. If you look at the Q numbers is 11580, and this number was 10700, and this Q is roughly 8.2% larger than the Q over here. So again, there's nothing surprising about it, because that surface area comes in the equation of the resistances of the total loss, J square into area. The surface area of the cylinder is smaller, and thus its Q is equivalently larger. So when you are trying to optimize the cavity, any cavity designs for the specific volumes you're looking for, just looking at the surface area and doing back of the envelope calculations or optimizations is a very, very good starting point. It helps you get to the answer very, very quickly. I think I'll stop here. Do you have any questions? I'll stop here for these cavities. I think we have finished all the cavity work we had to do. But do you have any questions?
Here we don't have any questions, sir.
Right, from the other class? All right, let's stop again. What I'll do tomorrow is I'll show you these cavities have become really important again. I'll show you some applications of these cavities beyond microwave engineering, beyond telecom engineering. These cavities are used in cyclotrons, for example, where you accelerate particles through electromagnetic fields. These cavities play an important role there. But in the recent times, over the last 5 or 6 years, these cavities have started to show up a lot in photonics too, especially for making sub-wavelength semiconductor lasers. Uh, these cavities are being used today, and I'll show you some of those applications. We won't do any maths. I'll just show you where they are coming up in the research areas these days, where they are being used a lot. Uh, they're being used in photonics for making sub-wavelength sensors, sub-wavelength lasers, and they are also used for making sensors, for making biochemical sensors. And in photonics area, the next question you probably would have asked, okay, we went from cube to a circle, a cylinder. Cylinder has a lower surface area, so the Q increases. Why don't we go to a sphere? Sphere has the lowest surface area possible for the same volume. The sphere should even give you better Q. Well, we don't go to sphere in metallic structures because it's difficult to make a metallic sphere. It's difficult to polish a metallic sphere around, and then it will be difficult to excite it too. However, in photonics, it's much easier to make spheres. It's very easy to make sphere. You take a piece of plastic, you melt the bottom, and you let that plastic fall due to gravity on the bottom. As it's falling below due to gravity, it automatically forms a sphere. You take an optical fiber, you melt the optical fiber, let a drop fall down in liquid glass form. The liquid glass form would become sphere in the air or any liquid, and you naturally create very interesting spherical cavities. And those spherical cavities actually have the world's highest Q factors. Q factors approaching 10 million have been achieved. I'll just connect you to these cavities in the modern day research where they are being used and how they are being used. We'll take a look at one specific cavity design which is called a ring resonator. No maths, just expand the knowledge beyond what is traditionally covered in a RF course, just to see its newer applications. Uh, so we have finished Unit 5. I will prepare questions and on Unit 5 and I'll send it to you guys. I won't be able to make the Saturday class, so we'll cancel the class on Saturday. I think Heather will send you an email confirming it. I won't be able to make Saturday's class. But next week, what do you suggest we do? We can do the problems. We can do a lot more problems than what for all the 3 units. Uh, the other suggestion I had was I can introduce you to a dielectric waveguide in one lecture, show you what a dielectric waveguide looks like, which is again the modern day waveguide. Uh, Mostly even in RF, a high speed RF, if you're going above 100 gigahertz, we are using dielectric waveguides. In photonics, we cannot use these metal waveguides. The loss is just too high. So we use dielectric waveguides there. So I can introduce you to dielectric waveguides. And I can also connect these topics we have learned here, to quantum mechanics. Because you see the very same effect in quantum mechanics too. And things like particle in a quantum well. I can connect those things without doing maths, just show you uh, why you would expect the solutions you get there. Would that be a good plan? Or do you want to do something else?
That would be okay, I suppose, sir.
All right then.
Problems.
Yeah, we can. I can send you some problems. We had sent you previous problems. We can take a look at some of the hard problems from there next week. And if after we have done the problems, if there is time left, then we can do. I can introduce the dielectric waveguide and its
Okay,
and then connect it to quantum mechanics.
sir.
Right? Tomorrow I
Yes,
just
sir.
connect these cavities to the modern day cavities being created without doing maths.
That would be fine.
All right. All right then. See you guys tomorrow.
Yes, sir.
And there won't be any class on Saturday.
Sir?
No class on Saturday.
Okay, sir.
All right.
I didn't get. I didn't get you, sir.
I said no class on Saturday.
Okay, sir.
I'm just sending you the message.
Yes.
No class on Saturday. Yeah.
Yeah. Okay, sir. Okay, that would be done.
All right.
And I've been talking about that blackboard detail. They will
Okay.
be giving it to me today.
All right. Send it to me, then I can.
So I'll mail you the details today,
Okay.
positively, so that tomorrow morning you can use the blackboard directly.
Okay. Good. Then I can just directly upload things and know what I've said and what I haven't said.
Yes, sir. That would be great.
Sure. All right then.
Yes, sir.
All
Thank
right.
you.
See you tomorrow. Then. Bye.
See you, sir.